May 2nd, 2026. A Saturday morning that began with a terrifying realization. Something broke. And I don't mean that metaphorically. What you are seeing isn't a typical eruption. There was no vertical plume reaching the stratosphere. No supersonic blast heard for miles. This was a structural collapse. Within seconds, millions of tons of superheated rock and gas turned into a pyroclastic density current, a wall of death moving at over 100 kilometers per hour, hugging the terrain, following the gullies as if it knew the geography of the villages below by heart. This wasn't supposed to happen. Not like this, and certainly not this early. According to every historical model we have, Mayon should have been in a stable, mid-level unrest stage. The official alerts said level 3. The press was filing stories about routine activity, but when scientists looked closer at the satellite record, they found a pattern that changed everything. A pattern that suggests our predictive models are failing. By the time you finish this nightly debrief, you will understand why the 100,000 people currently living in the shadow of this mountain are facing a countdown that no one is talking about. Because the May 2nd collapse wasn't the disaster. It was the loading of the system. And the trigger isn't coming from the volcano. To understand the danger currently unfolding at Mayon, we first have to address a common perceptual bias. When we see a volcano on the news, our eyes are naturally drawn to the spectacular. The fountains of orange lava, the glowing rivers of molten rock snaking down the slopes. We are biologically hardwired to fear the fire. But in the world of investigative meteorology, we know that lava is often a secondary concern. Lava moves slowly. It is predictable. You can usually walk faster than a lava flow can travel. The real threat, the one that catches communities off guard, is far more violent and infinitely faster. It is the pyroclastic density current, GPDC. The press coverage of the May 2nd event treated it like a minor expression of volcanic unrest. They focused on the visual ash fall and the temporary displacement of a few thousand people. They framed it as a volcano simply doing volcano things. By treating this as a routine event, the mainstream narrative misses the most critical diagnostic signal. The May 2nd collapse was not a release of excess pressure. It was a structural failure. It proves that the mountain's integrity is being compromised from within. And the most dangerous part of a volcanic crisis rarely looks like the footage you see on the evening news. The real killer is often silent, gray, and completely misunderstood. Let's look at the raw data from that Saturday morning. This was not a small NOAA event by any scientific metric. At exactly 5:30 a.m., a massive block of accumulated lava and dome material on the southern flank lost its battle with gravity. As it shattered, it didn't just fall, it pulverized. The temperature, the internal core of the flow, exceeded 500 degrees Celsius, 932 degrees Fahrenheit. At these temperatures, the air itself becomes a weapon. The runout. The current raced 4 kilometers down the Basud Gully. This is a natural highway of destruction, carved by centuries of previous eruptions. The speed. It moved at over 100 kilometers per hour, creating a pressure wave in front of it that can flatten structures before the heat even arrives. The human cost. The immediate fallout was staggering for an event labeled as mid-level unrest. 52 villages were blanketed in thick, abrasive volcanic ash. 3,000 residents within the permanent danger zone had to be evacuated in a matter of hours. In total, over 102,000 people found their lives upended by a collapse that lasted less than 10 minutes. The ashfall caused total blackout conditions in parts of Albay. Visibility dropped to zero. Agriculture, the lifeblood of this region, was devastated as ash choked the crops. But here is the most unsettling part of the investigation. While the world was watching the footage of the May 2nd collapse, the data suggests that this event didn't actually start in May. To find the true origin of this collapse, we have to go back 5 months, to a piece of data hidden in the NASA archives that everyone else chose to ignore. While the international press was focused on the dramatic footage of the May 2nd collapse, the true story, the one that reveals the systemic shift in our planetary behavior, was hidden in the infrared spectrum. To understand why Mayon is failing now, we have to look at the data that was quietly accumulating in the NASA archives long before the first rock fell. This is where we introduce the invisible eye, MIROVA. Standing for Middle Infrared Observation of Volcanic Activity, this monitoring platform uses the MODIS sensors on NASA's Terra and Aqua satellites. It doesn't look at smoke, it doesn't look at ash. It looks at volcanic radiative power, VRP, the actual thermal energy being emitted by the mountain's core, the timeline of escalation. When we reconstruct the last 5 months, a terrifying pattern emerges. This wasn't a sudden awakening. It was a calculated mechanical climb. Late December 2025, the silent baseline. For years, Mayon's thermal signature was subdued, showing only background noise. But in the final week of December, the first anomalies appeared. They were small, almost apologetic readings, but they were the first signs that the magma reservoir miles beneath the surface was being recharged. January, February 2026, the foundation of chaos. By January, the anomalies became consistent. This wasn't just heat, it was physical displacement. During this 2-month window, sensors recorded 9,941 rockfalls and 1,346 volcanic earthquakes. Investigative insight. Rockfalls are the mountain's way of screaming. Each one represents a fracture in the structural integrity of the cone as magma forces its way upward, expanding the rock like an overinflated tire. March 2026, crossing the moderate threshold. In March, the radiative power readings crossed into the moderate category. The staircase had taken its first clear step. The summit was now hot enough to be detected through heavy cloud cover day and night. April 2026, the very high alert. This is the month everything changed. In April, MIROVA began recording very high thermal anomalies. This is a diagnostic threshold associated with active lava effusion and substantial subsurface heat flux. While the public saw a quiet mountain, the satellites saw a system nearing its breaking point. The smoking gun, $SO, $2 degassing. Beyond the heat, there was the chemical signature. In the weeks leading up to the May 2nd event, sulfur dioxide, $SO $2 emissions, a direct indicator of fresh magma approaching the surface, hit a staggering peak of 6,569 tons per day. For context, the baseline for a restless volcano is often under 500 tons. This massive surge in degassing tells us that a massive volume of gas-rich, new magma had moved into the upper conduit. It was chemical proof that the balloon was being inflated faster than the pinhole of the vent could release it. What makes the 2026 cycle so anomalous is the stair-step escalation. In traditional models, volcanic activity spikes and then returns to a baseline. But at Mayon, every month in 2026 has established a new, higher baseline. The system is not resetting after each event. It is accumulating energy. This wasn't a series of random events. It was a 5-month staircase of energy accumulation, where the rate of input from below was significantly higher than the rate of expression at the surface. But if the energy was building for 5 months, why did it choose the southern flank to break? And why did it happen with such violence on a morning when everything seemed normal? To answer that, we have to look at the unique, high-pressure chemistry of the mountain itself. To understand why the southern flank of Mayon simply gave up on May 2nd, we have to look past the surface and into the plumbing of the volcano itself. This isn't just about heat. It is about a specific, high-stakes chemical battle happening miles beneath the Albe soil. Mayon is not a basaltic volcano like those in Hawaii, where lava flows like thin syrup. Mayon is an andesitic stratovolcano. In the world of geology, andesite is the middle ground. It has a high silica content, roughly 57%, to 63% by weight. This silica creates a molecular backbone that makes the magma incredibly thick and viscous, the silica wall. Because the magma is so thick, it doesn't just erupt, it struggles. It behaves like cold honey being forced through a narrow straw. As the fresh magma recharge that we identified in our 5-month satellite record moves upward, it carries a massive load of volatiles, water vapor, carbon dioxide, and that critical 6,569 tons of sulfur dioxide we tracked in April. In a healthy Gamki volcanic system, these gases bubble out and escape into the atmosphere. But in an andesitic system under pressure, the gases get trapped. The viscosity of the magma acts like a seal. The bubbles form, they expand, but they cannot migrate through the thick melt fast enough. Imagine inflating a heavy-duty industrial tire that has no relief valve. Every ton of gas pumped in increases the internal structural tension. The mountain isn't just a volcano anymore. It has become a planetary-scale pressure cooker. As this overpressurized magma reaches the summit, it creates what volcanologists call a lava dome, a massive, rigid plug of cooling rock sitting directly in the throat of the volcano. While the press was filming lava flows, what was actually happening was structural loading. Because the lava was too thick to flow freely, it began to pile up on the upper southern flank. Mayon's slopes are famously steep, nearly 40 degrees. This is right at the limit of what gravity allows for loose material. For 5 months, the volcano was loading the system, stacking millions of tons of heavy gas-charged rock on a 40-degree incline. The failure of the internal skeleton. The internal skeleton of a stratovolcano is made of alternating layers of old lava flows and loose ash. It is not a solid block of granite. It is a layered composite, like a stack of loose papers. By late April 2026, the data shows that the sheer weight of the new lava combined with the internal gas pressure pushing outward from the conduit reached a threshold crossing. The system wasn't releasing energy through the top. It was storing it in the walls. The May 2nd event wasn't an explosion because the gas couldn't break the seal of the dome. Instead, the seal was so heavy that it broke the mountain. This is the anatomy of chaos. The system was being overcharged, and the structural integrity of the southern flank was the first thing to fail. It was the physical limit of geology meeting the relentless input of a planetary system in transition. But what happens when that massive overpressurized plug finally falls? When the lid of the pressure cooker slides off the side. To see the true violence of that moment, we have to reconstruct the exact seconds when the mountain gave way. At 5:30 a.m. on May 2nd, the internal architecture of Mayon reached its absolute mechanical limit. For 120 days, the mountain had acted as a containment vessel for an escalating magmatic intrusion. But as we've established, the system was no longer venting pressure through the summit in a traditional vertical column. Instead, it was storing that energy as physical mass, stacked precariously on a 40-degree incline. The mechanics of the break. In the world of structural geology, there is a constant battle between shear stress, the force of gravity pulling material down, and shear strength, the internal friction holding the mountain together. On May 2nd, the weight of the accumulated lava dome finally exceeded the friction of the underlying rock layers. This was not a volcanic blast in the way Hollywood portrays it. It was a structural surrender. The mountain didn't explode outward from internal gas expansion. It shattered downward because it could no longer support its own weight. The massive plug of cooling andesite, hundreds of meters thick, simply detached. As it slid, the sudden removal of that lid caused the gas-rich interior of the dome to fragment instantly, a process called autobrexiation. In a heartbeat, solid rock turned into a fluid-like suspension of superheated gas and pulverized glass. It didn't explode from the vent. It gave way from the Suon flank. The mountain didn't lose its breath. It lost its skeleton. The domino effect. As the dome collapsed, it took a portion of the older underlying crater rim with it. This is why the May 2nd event is classified as a flank collapse. The resulting pyroclastic density current, PDC, was fueled by the potential energy of height and the thermal energy of the trapped gases. The satellites recorded a massive thermal spike as the interior of the dome was exposed to the atmosphere. This wasn't just a landslide, it was a flash boiling of geological material. The 4-kilometer runout was the direct result of the sheer volume of material involved, a volume that had been meticulously loaded onto the slope by the 5-month escalation sequence we tracked in the NASA records. The shift in reality. For the residents of Albay, the morning of May 2nd was a chaotic awakening of ash and thunder. But for the analysts watching the data, it was a profound shift in the risk calculus. The collapse of the dome has changed the geometry of the summit. The plug is gone, but the magma recharged from depth, the engine driving this entire cycle, has not stopped. Seems a structural failure of this magnitude is a threshold crossing. It proves that the mountain is no longer capable of containing the energy being pumped into it. The May 2nd event wasn't the climax. It was the first crack in the dam. And this changes everything. Because when we compare this specific sequence of failures to the major eruptions of 2018 and 2023, the data tells us that we are moving into uncharted territory. The cycle isn't just repeating, it's accelerating. To determine the severity of what comes next, we must move beyond the events of May 2nd and look at the broader historical architecture of Mayon's activity. In volcanology, we don't just look at eruptions, we look at envelopes of behavior. When we compare the 2026 sequence to the major crises of 2018 and 2023, the data reveals a chilling trend. We are no longer witnessing a repetition of the past. We are witnessing cycle compression. The interval between Mayon's major unrest periods is shrinking. Between the 2018 and 2023 episodes, the system had 5 years to recover and recalibrate. But the current 2026 cycle arrived less than 3 years after the 2023 event subsided. This is the compression phase. When a volcanic system cycles faster, it often indicates that the magmatic plumbing underneath is becoming more efficient. The pathways from the deep reservoir to the surface have remained warm and pressurized, allowing new magma to ascend with less resistance. In 2026, Mayon didn't need to wake up. It never truly went back to sleep. Even more concerning than the timing is the intensity. Let's look at the physical evidence. Runout. Lengths. In the 2023 crisis, which was considered a significant event, lava flows reached a maximum length of 2.8 kilometers. In the first 4 months of 2026, the Basud Gully has already seen lava flows extending to 3.8 kilometers. The PDC magnitude, the pyroclastic density current on May 2nd, reached the 4 kilometers mark instantly. In 2018, it took weeks of escalating alert level 4 activity to produce PDCs of this scale. In 2026, the mountain achieved this level of violence while still classified under moderate unrest. Soon, the baseline has shifted. What we once considered peak activity in 2023 is now the starting point for 2026. The system isn't just active, it is accelerating. Think of Mayon's energy as a staircase. In previous decades, the volcano would climb a few steps, release energy, and return to the ground floor. But since late 2025, the mountain has refused to descend. Each month, January, February, March, April, has served as a higher landing. The May 2nd collapse was simply the first time the system stepped onto a floor that the public could see. But for those of us monitoring the volcanic radiative power, the climb has been visible for 5 months, and we are witnessing a threshold crossing. The 2026 cycle is moving faster, reaching further, and storing more energy than any comparable period in the modern satellite record. The perfect cone is no longer behaving according to the rules of the last century. But what is driving this acceleration? If the surface expression is already this violent, What is happening in the one place our satellites cannot see? To find the engine of this crisis, we have to go deeper, miles below the crust, into the invisible factor. While our satellites have spent 5 months documenting the escalating heat at Mayon summit, the true architect of this crisis remains hidden. To understand the why behind the May 2nd collapse, we must look where no camera can reach, into the dark, high-pressure plumbing miles beneath the Philippine crust. This is the invisible factor, a sustained magmatic recharge that has been systematically priming the volcano for a catastrophic failure. Mayon does not exist in isolation. It is a product of one of the most violent tectonic interactions on Earth. To the east, the Philippine Sea Plate is sliding beneath the Eurasian Plate at a rate of several centimeters per year. As this oceanic crust descends into the hot mantle, it carries with it a lethal cargo: seawater and carbon dioxide trapped within the rock. At a depth of approximately 100 kilometers, the intense heat forces these fluids, or volatiles, out of the plate and into the overlying mantle wedge. These chemicals lower the melting point of the surrounding rock, creating the magma that eventually feeds Mayon. This is the planet's ultimate power cord, and in 2026, the current is running at full capacity. Geologists no longer view volcanic reservoirs as simple tanks of liquid fire. Instead, beneath Mayon sits a magma mush zone, a complex, sponge-like network of crystals and molten rock. Our analysis of the 1,346 volcanic earthquakes recorded between January and April 2026 reveals a telltale signature. These aren't just rocks breaking. Many are long-period LP earthquakes, which indicate the movement of pressurized fluids through the deep conduit system. The earthquakes were the sound of the pump. For 5 months, fresh, hot, gas-rich magma has been intruded into the shallower reservoir, overpressurizing the mush zone and forcing the system towards its mechanical breaking point. As we discussed in Chapter 5, Mayon's andesitic magma is thick and viscous. When the deep recharge hits the shallower levels, the temperature of the system rises, but the pressure rises even faster. Because the magma is too thick for gas bubbles to escape easily, the entire upper conduit becomes a giant piston. The May 2nd collapse was the system's attempt to resolve this pressure through structural failure. But here is the unsettling truth that the invisible factor reveals. The recharge has not stopped. The deep seismic signals and the sustained volcanic radiative power, VRP, captured by NASA satellites, suggest that the pump is still running. The material removed during the collapse on May 2nd has simply created more room for new, fresh magma to fill. The system is being reloaded in real time. Everything dangerous about the May 2nd event was driven by processes happening miles underground. But the most uncomfortable fact in this investigation is that the invisible factor is only the setup. The engine is underground, but the weapon is already on the surface. You have seen the fire, you have seen the heat, but the data from the last century tells a different story about how Mayon actually kills. To find the real threat, we have to look away from the magma and towards something far more common, far more misunderstood, and infinitely more deadly. We have spent this entire debrief analyzing the fire, the heat, and the structural collapse of Mayon's cone. To the untrained eye, these are the ultimate symbols of volcanic destruction. But the historical record of this mountain and the data from our own recent planetary shifts tells a far more chilling story. In the world of investigative meteorology, we look for the silent killer. And at Mayon, that killer isn't molten rock. It is lahar, the historical calibration, 1993 versus 2006. To understand why your concern should be shifting from the summit to the riverbanks, we must look at 2 specific dates. 1993, the direct strike. In 1993, Mayon erupted with terrifying violence. It sent pyroclastic flows directly into populated areas. It was a worst-case eruptive scenario. The death toll was 79 people. It was a tragedy that reshaped Philippine disaster protocols. 2006, the invisible catastrophe. 13 years later, the volcano was winding down. The eruption was technically over. But then came Typhoon Reming. The rain interacted with the fresh ash left on the slopes, and the resulting lahars didn't just strike, they erased entire communities. The death toll was over 1,266 people. Sadru, in the modern record, the water has killed 16 times more people at Mayon than the fire ever did. The real danger doesn't start with the eruption. It starts when we think the eruption is over. A lahar is often mistranslated as a mud flow. This is a dangerous simplification. Mud is soft. Mud is slow. A lahar is a high-density slurry of volcanic debris, boulders, and water. Density. A typical lahar has a density of $2, $0 to $2.50 /text-G cm. Circumflex. $3. This is roughly the same density as wet concrete. Viscosity. Because of its high sediment load, it doesn't splash, it grinds. It has the fluidity of water, but the momentum of a freight train. Behavior. It flows through buildings, not around them. It buries houses to their rooflines in seconds, and once it stops, it solidifies like a rock. You cannot swim in it, and you cannot outrun it in a confined valley. What we are witnessing in the first half of 2026 is a massive multi-month loading phase. Every one of the 1,690 pyroclastic density currents we tracked since January has deposited a layer of loose, fine-grained ash on the steep slopes. Every rockfall has added to the inventory of mobile material. The May 2nd collapse was the single largest delivery of fuel to the lower slopes. It didn't just scare 3,000 people away. It deposited millions of cubic meters of fresh, unconsolidated material directly into the Basud, Bonga, and Miaisi gullies. Aciderd. The volcano has spent 5 months loading the slopes. It has placed the ammunition exactly where it needs to be, in the high-speed channels that lead directly to the river valleys of Albay. The volcano has done its job. It has loaded the system. But ammunition is useless without a trigger. And as we look at the meteorological data for the coming months, we see that the trigger is already being pulled. To understand how the geography itself has been pre-wired for destruction, we have to look at the landscape ready to fail. Mayon is often celebrated as the most perfect volcanic cone in the world. Its near-flawless symmetry is a marvel of geological engineering, a steep-sided monument rising 2,462 meters above the Albay Gulf. But in the world of investigative meteorology, that symmetry is viewed through a different lens. To us, Mayon's perfection is its greatest structural liability. It is a geometric trap. The mountain's steepness is the primary driver of its destructive potential. The upper slopes of Mayon maintain an angle of approximately 40 degrees. At this incline, gravity is no longer a passive force. It is an active accelerator, but it's the surface of the cone that houses the true danger. Mayon is scarred by more than 40 ravines, deep, jagged gullies that radiate from the summit like spokes on a wheel. These are not just geological features, they are high-speed highways of death. The primary channels, the Basud, Bonga, and Miaisi gullies on the southern and southeastern flanks are the most critical. These channels are the natural conduits for everything the volcano produces, the accelerator effect. Because the slopes are so steep, any material, whether it is superheated gas or rain-soaked ash, is instantly funneled into these narrow ravines, concentrating its mass and increasing its velocity as it screams toward the lowlands. Ito, the mountain is pre-wired for disaster. Every ravine you see on the satellite map is a pre-cut path designed by nature to deliver volcanic material directly to the front doors of the Albay floodplain. By early May 2026, the inventory of material sitting in these ravines has reached a critical volume. For 5 months, the volcano has been loading the gun. Unconsolidated material. We are looking at millions of cubic meters of fresh ash, lapilli, and fragmented lava. This material is unconsolidated, meaning it has no root systems to hold it in place and no internal cohesion. It is simply a loose pile of mineral ammunition resting on a 40-degree slope, the saturation threshold. Because this fresh ash is highly porous, it can absorb a massive amount of water. But once it reaches its saturation point, the internal friction between the grains vanishes. The entire mass shifts from a solid state to a liquid state in seconds. The tragedy of Mayon is that people live exactly where the ravines lead. The river systems, the Padang, the Yawa, the Kinali, and the Inarihan all originate at the base of these volcanic gullies. For centuries, the volcanic soil has made this land incredibly fertile. This fertility has drawn millions of people into the floodplains. But these floodplains are the terminal points for every lahar. Modern human infrastructure, our bridges, our dikes, and our concrete homes, is designed to withstand water. But as we established in Chapter 9, a lahar is not water. It is liquid concrete. Our dikes are built for floods, but when the Padang River fills with 1 million tons of volcanic slurry, the dikes don't stop the flow. They become the walls of a channel that directs the destruction deeper into the heart of the city. The landscape is loaded. The ravines are primed. The river valleys are populated. Every physical variable required for a catastrophic event is now in place. But there is a human element to this equation that the satellite data cannot capture. To understand the true stakes of the coming weeks, we have to look at the people caught in the middle and why, for them, evacuation is not a solution, but a terrifying delay. In the cold clinical world of satellite telemetry and thermal radiative power, the events of May 2026 are measured in megawatts and cubic meters. But on the ground, the anatomy of chaos is measured in heartbeats and hard choices. To truly understand the crisis at Mayon, we must analyze the most complex data point in the entire system, the human variable. Why do people live in the shadow of a mountain that has tried to erase them for 4 centuries? The answer is a brutal intersection of geology and economics. Volcanic soil is among the most fertile on Earth, enriched by the very ash that periodically destroys it. For the farmers of Albay, the volcano is both the provider and the executioner. The permanent danger zone, PDZ. A 6-kilometer radius around the summit is officially designated as uninhabitable. Yet, the data shows that thousands of people remain within or on the immediate fringes of this zone. Economic displacement. These aren't people choosing risk. They are people managed by necessity. Their livestock, their crops, and their ancestral ties are anchored to this soil. Leaving isn't just a relocation. For many, it is a total loss of identity and survival. When the collapse occurred on May 2nd, the evacuation was hailed as a success. Over 3,000 residents were moved to temporary shelters within hours. But as an investigator of long-form disasters, I must ask, what does safety actually look like? Evacuation centers, often local schools or community gyms, are designed for short-term emergencies. But a volcanic crisis in the 2026 escalation cycle is not a short-term event. We are witnessing a sustained displacement, the school paradox. In many villages, schools become shelters. This means education stops. The social infrastructure of the community begins to fray. The resource strain. Feeding and providing sanitation for 3,000 people in a temporary facility for weeks or months creates a secondary crisis of health and morale. Keyline. Evacuation isn't a solution, it's a delay. It is a tactical retreat in a war where the enemy doesn't sleep and the front lines are determined by gravity. There is a specific phenomenon we observe in communities living near high-frequency volcanic systems: risk normalization. When a mountain produces nearly 10,000 rockfalls in 4 months, the residents begin to tune out the sound. The spectacular becomes mundane. This creates a dangerous gap in the risk calculus. People see the pyroclastic flows on May 2nd, they evacuate, and then they wait. As the days pass without a massive explosion, the urge to return, to check on the cows, to salvage the crops, becomes overwhelming. Once, the human spirit is remarkably resilient, but in the face of a system in transition, that resilience can become a liability. The people are waiting for the volcano to stop, but the satellite record tells us the volcano is just getting started. Finally, we must address the physical fragility of our modern world. We build power grids, telecommunications towers, and paved roads to create a sense of permanence. But as we saw in the ashfall of May 2nd, a few millimeters of volcanic glass can cripple an entire province's electrical grid. In the 2026 cycle, our technology is not protecting us. It is merely providing us with a clearer view of our own vulnerability. We can track the magma, we can map the ravines, but we cannot move the cities. The people have been moved. The shelters are full. The waiting has begun. But as the calendar turns toward June, the atmosphere is preparing to introduce a variable that no evacuation center can withstand. We have reached the most critical juncture of our investigation. To this point, we have analyzed Mayon as a geological entity, a machine of magma, pressure, and structural failure. But a volcano does not exist in a vacuum. It exists within an atmosphere, and as the calendar turns, the geological timeline of the 2026 escalation is about to collide head-on with the meteorological timeline of the Western Pacific. This is the countdown. As of early May, the Albay region is standing at the doorstep of the southwest monsoon, or habagat. In the Philippines, the period from June through October is not merely rainy, it is a season of atmospheric bombardment. The region receives an average annual rainfall of 2,500 mm to 3,000 mm, with the vast majority compressed into these 5 months. For the loaded slopes of Mayon, the rain is the ultimate mechanical trigger. When moisture infiltrates the fresh, unconsolidated ash deposits we tracked in Chapter 4, the internal physics of the slope change. Water acts as a lubricant, increasing the pore water pressure and reducing the shear strength of the debris to nearly zero. Based on our investigative modeling, we are looking at 3 distinct branching scenarios for the next 60 to 90 days. Scenario 1, the chronic erosion, the silent leak. Even without a major storm, steady monsoon rains can trigger small-scale lahars. These nuisance flows fill irrigation canals and deposit thin layers of silt on farmland. While not immediately deadly, Scenario 1 creates a false sense of security, slowly clogging the drainage gullies and making the system more prone to overflowing when a larger event occurs. Scenario 2, the massive mobilization, the 2006 repeat. This is the typhoon scenario. A direct hit or a close pass by a Category 3 or higher storm can deliver 500 mm to 700 mm of rain in 24 hours. Under these conditions, the entire 5-month inventory of ash and rock on the southern flank, millions of cubic meters, will mobilize at once. This is the wet concrete event that can bury entire towns like Guinobatan or Padang. Scenario 3, the compounding disaster, the nightmare. In this scenario, a major structural collapse, Phase 2, occurs during an extreme rainfall event. The mountain fails, generating a pyroclastic flow that is immediately saturated by torrential rain. This creates a hot lahar, a boiling slurry of rock and water moving at over $80 to hext km h dollar. This is the ultimate expression of compounding disasters, where the geological and atmospheric systems synchronize to produce maximum lethality. We are currently at T-minus 30 days before the atmospheric pump begins to prime the slopes. Every day the eruption continues to load the mountain, the ammunition for Scenario 2 and 3 grows. D, the volcano has done its part. It has provided the mass, the heat, and the slope. Now the atmosphere is moving into position to pull the trigger. The only thing missing from this catastrophe then is the water. Sindut, In investigative meteorology, we don't look for if, we look for when. The rain in Albay is not a probability, it is a seasonal certainty. We are watching a slow-motion collision between a loaded mountain and a coming storm. The data is lining up, the history is clear, and the geography is unforgiving. As we enter the final minutes of this nightly debrief, we must face the uncomfortable conclusion of the 2026 Mayon crisis. We have reached the end of our debrief, but for the residents of Albay, this is where the true vigilance begins. Throughout this investigation, we have stripped away the cinematic spectacle of Mayon to reveal a cold, mechanical reality. We are not just watching an eruption, we are watching a planetary machine in the process of state transition. Let's bring all the data points from our investigation together. In the world of investigative meteorology, we do not view these variables as separate events. They are part of a single, integrated physical argument. The greatest threat to human life at Mayon in the coming weeks is not the volcano's violence, it is our own perceptual fatigue. As the days pass without another massive collapse like the one on May 2nd, the Alert Level 3 status will begin to feel like the new normal. The news cycle will move on to the next global anomaly. But as we have proven through the satellite record, Mayon's energy is not dissipating. It is being stored. And the absence of an explosion is not the absence of danger. In a loaded system, silence is merely the sound of the trigger being slowly squeezed. The big idea: fire loads, water triggers. As we close this report, I want you to remember one phrase that summarizes the entire physics of the 2026 Mayon crisis. The volcano loads the system, the rain pulls the trigger. The fire, the magma, and the pyroclastic flows has spent 5 months meticulously placing millions of tons of debris on a 40-degree incline. It has done the heavy lifting. It has prepared the landscape for failure. Now the fire can stop. The volcano can go silent tomorrow, and it would not change the risk calculus. The Western Pacific atmosphere is now in control. The moisture is moving in. The typhoons are forming. And when that water hits those loaded slopes, the fire will be replaced by the grinding, relentless power of the lahar, the misunderstood killer, that historically claims far more lives than the lava ever could. The global perspective. Mayon is a microcosm of a much larger shift. Across the planet, from the weakening magnetic fields to the slowing of the AMOC currents, we are seeing the old rules of forecasting dissolve. Human infrastructure, our dikes, our cities, our evacuation protocols, is designed for a world that no longer exists. We are entering an era of compounding disasters, where geology and meteorology no longer operate on separate schedules. We are watching this build in real time. We see the thermal anomalies, we see the staircase escalation, and we see the communities caught in the crosshairs. If you are watching this from the Bicol region, or if you have family in the shadow of Mayon, drop a comment below and tell us which river system you are monitoring. Whether it's the Padang, the Yawa, or the Kinali, your eyes on the ground are the final layer of this investigation. The data is public. The pattern is documented. The clock is running. Stay vigilant. Stay grounded in the data. And most importantly, stay prepared. This has been a Plasma Pulse Nightly Debrief. We will continue to monitor the thermal record. Good night.